Thank you for viewing this presentation. Today I'm going to talk about Lidar observation of instability and vertical eddy diffusivity induced by gravity wave breaking in the Arctic mesosphere. So in this presentation, I'm going to present 4 case studies where consistent spreading and overturning are found in sodium and potential temperature environments. Meanwhile, consistent gravity wave signatures are found in both sodium and really Lidar measurements, and these waves are observed to disappear at the height of the overturning. We developed a turbulent transport model to explain the observed diffusion and estimate the turbulent diffusion coefficients and energy dissipation rate. Also, the energy dissipated by the gravity waves are investigated as possible source for turbulence generation. We're going to use the case observed on 18-19 October 2018 as a detailed case to illustrate the theory and method used in this study. We'll then present a comparison of all the cases. So here are the details of the 2 Lidar systems that are used in this study. One of them is the sodium resonance wind temperature Lidar, and the other one is the radial density temperature Lidar. So here's an overview of the first case. We show the sodium density, temperature, meridional wind, and potential temperature and sodium mixing ratio in this slide. We notice that there is a overturning signature in the sodium density measurement, and meanwhile we can see strong negative temperature gradient and strong wind shear at the same time and height. More importantly, we have 2 independent tracer, potential temperature and sodium mixing ratio, show very consistent structure of broadening and sharpening in the contour. Meanwhile, we can see in all plots signature of upward propagating gravity waves that are relatively continuous below 90 kilometers and then appear to be disrupted above 90 kilometers. So to investigate the instability and vertical diffusion in detail, in this plot we show the vertical gradient of potential temperature derived from different temporal and vertical resolution, as well as the vertical profile of sodium mixing ratio and sodium density. In the profiles of potential temperature, we see that first, the reduction of stability around 87 km exists no matter what temporal or spatial scales are used. Although the 0.5 km and 1 km profiles, which are the red and the black profiles in each plot, show inconsistent results if we vary the temporal resolution, while the 2 km profile, which is the blue profiles in each plot, show very consistent structure. Therefore, in this study, we're going to choose the 2 km profiles to identify the less stable or sometimes unstable layers. In the profiles of sodium, we have clearly a layer where the sodium mixing ratio is diffused and the sodium density is overturned. We notice that the layer of diffusion is wider than the layer of instability. So in the mesosphere, layers of instability and diffusion are often associated with gravity wave breaking. So in the next few slides, we're going to investigate the vertical evolution of the gravity waves at this night. In the left plot, we show the sodium temperature perturbation and Rayleigh density perturbation measured on this night. We can see clearly signatures of upward propagating gravity waves below 90 kilometers, and then the straight signature appears to disappear above about 90 kilometers. On the right side, we show the frequency spectra of sodium density and temperature. Again, we see what appears to be about a 5-hour wave below 90 kilometers, and this wave disappears around above 90 kilometers. It turns out the exact period of this wave is 5.6 hours. So we did a harmonic fit of 5.6 hours to the different measurements, sodium density, temperature, meridian wind, and the Rayleigh density. And we show the gravity wave amplitude and phase in these figures. Clearly, in all measurements, the amplitude of this wave saturates around about 87 kilometers. Meanwhile, in all plots that shows data above 90 kilometers, we see that the phase progression is reverse. Both signatures suggest that this wave breaks at this height, which is about 87 kilometers. So to summarize, we have seen that diffusion and vertical diffusion and stability coincide with gravity wave breaking at this night. In the next few slides, we're going to use a turbulence transport model to explain the diffusivity and estimate the strength of turbulence. So our model simulates that the turbulence was generated, which induced a perturbation to the sodium density. This perturbation is counteracted by the chemistry. At this point, which is the local maximum of the variation, the two terms balance, and from the balance we can estimate the strength of turbulence. I leave out a lot of math in here given the limited time. But to estimate the turbulent diffusion coefficients, we need these four parameters, and we can directly get the HF, alpha, and tau as these values, and then the only parameter that's left is the value of L. There are two apparent methods to estimate the value of L. One is from the depth of the layer of diffusion, and the other is the depth of the unstable layer. These two estimates give very different values. One of them gives a value of 3.5 kilometers, and the other gives 0.78 kilometers. We estimate two different eddy diffusion coefficients based on these values, and then we can estimate the energy dissipation rate given the n square values as these numbers. We will discuss which of the two numbers are more reasonable in later slides. So now we investigate the gravity wave as a source of energy for turbulence generation. So in this plot, the blue profile shows the vertical profile of the potential energy of ensemble of gravity waves, meaning all the gravity waves, while the red profile shows the potential energy of the 5.6 hour monochromatic gravity wave. From the blue profile, we estimate the energy dissipated by gravity waves in the following using the following method. First, we estimate the potential energy at the bottom of the layer, and then we estimate the energy at the top of the layer. If the gravity waves are freely propagating, the potential energy should grow at the scale height of the atmosphere. So the energy dissipated by the waves can be estimated by the difference of the freely propagating wave and the observed wave. So the time scale of the energy dissipation rate is then estimated by the depth of the layer divided by the group velocity, vertical group velocity of the waves. We estimate a energy dissipation rate by gravity waves of 36.6 milliwatts per kilogram, which is larger than the value we estimated in the last slides. Meanwhile, the average energy of the monochromatic wave over the layer of diffusion is this value, and we assume that this energy is totally dissipated because it's very clear that the wave the energy goes to a very low value, which is very close to zero. Using the group velocity and the depth of the layer, we can estimate the energy deposited by the monochromatic wave at 35, which is also larger than the energy dissipation rate of turbulence. So, comparing the two profiles in the last slides, it is very clear that the monochromatic wave is much more dissipated than the assembled gravity waves. In addition, as we can see in the previous slides, the raw perturbation showed both the raw perturbation and the frequency spectrum show that the 5.6 hour monochromatic wave dominates the gravity wave variation in the MLT region for this case. So this evidence leads us to believe that the energy deposited by the monochromatic wave is more likely the source of turbulence generation. Now we compare the results from all the cases. So the value on square, K and epsilon are listed for all the cases. Considering the first three cases which are observed at similar heights, we can see that the larger eddy diffusion coefficients correspond to smaller n squared, which is consistent with the physics of turbulence, where less stable atmosphere is more likely to generate stronger turbulence. The only exception is the case which is observed at a lower height. We also investigate the gravity waves as source of turbulence for the other case in 2018. For this case, the assembled gravity wave, the energy from assembled gravity waves is much smaller than that from the monochromatic waves. So we conclude that for both cases, the monochromatic wave is more likely the source of energy for turbulence generation. So in this plot, we compare the estimated value of eddy diffusion coefficients and the energy dissipation rate with other in situ rocket-borne measurements of turbulence in the Arctic region. For the estimate of turbulence using the depths of the unstable layers, the value of K are slightly larger than the other measured values, which are the red circles, while the value of epsilon are in good agreement with the other measurements. However, when we use the depths of the layers of diffusion, both values of K and epsilon becomes larger, which leads to much larger K and good agreement epsilon. So this comparison suggests that we should use the instability layer depths, which are smaller than the depths of diffusion layer, as the depths of turbulence, because it keeps the value of K in good agreement and also keeps the epsilon in good agreement with other estimates. So here are our conclusions. We have investigated the instability, diffusion, and gravity braking, and we estimate the turbulence. The values are in better agreement with other rocky measurements, if we use the depth of the unstable layer, we have larger values k found correspond to lower values of n squared. This highlights the importance of characterizing environment conditions when obtaining turbulence measurements. The fact that gravity waves are dissipating for these cases, and we find that monochromagnetic wave is more likely the source of turbulent generation for the two cases.